Hello and welcome to another episode of the OPELX podcast. This is a part of the Open Power Electronics project, or OPELX for short. Visit us online at opelex.net. That's opelex.net for past episodes, show notes and more. This podcast is hosted by me, Lalit Patnaik. Currently, I am a power electronics engineer at AVL in Graz, Austria.
And I am Abhijit Kshirsagar, currently a faculty member at IIT Dharwad in northern Karnataka. Critical support behind the scenes comes from Sudarshan Karthik and Najat Abdul Aziz. In this podcast, we talk to leading experts in academia and industry in power electronics and allied fields. We hope you find this useful and entertaining.
Hello everyone and welcome to the next episode of the OPELX podcast. Today we have Mr. Atul Abhyankar, who is from L&T Technology Services. This is Larsen & Toubro, which is very, very well known all across India and outside as well. He is currently having this very interesting designation of practice head in power electronics. So hello and welcome Mr. Abhyankar, and please introduce yourself to us in a more elaborate way, especially explaining this meaning of the designation practice head, because it's quite unique for us.
Sure. So first of all, thank you Abhijit, Lalit and Sudarshan for this opportunity, and gives me a lot of pleasure to be associated with OPELX and be a part of this session with you. Mm-hmm. So yes, it's an interesting designation of being a practice head. So we are a services company. I'm a part of Larsen & Toubro Technology Services, where we are into various domains like industrial, automotive, aero, process engineering, medical, high-tech, telecom, so on and so forth. So power electronics is a common bond, which is actually a growing field in all these domains. So as a part of the power electronics practice, I handle all the power electronics activities mainly with the industrial segment, where we see the most of it, and also work with the automotive segment to help and solution the power electronics, especially in the EV side, and with the aero to help them with the hybrid aircraft. And of course, in the industrial side with electrification, with the drives, with telecom power supplies, and general power conversion, where power and utilities, where you need a lot of power electronics domain. Mm-hmm. So that's where the whole thing comes from. And I head the practice which helps us ideate, architect the solutions in power electronics, and also work with the customers to agree to what kind of a solution they would have before we proceed on the project. Lalit?
Mm-hmm. Yeah, so you have like various industry segments from which you would have companies as your customers.
Yes, absolutely. So we have companies from drive segment, some leading drives players from the US. We have some leading tier ones for automotives from US, Europe and Japan too. Even the OEMs from Europe and Japan. And also we have a lot of power and utilities companies from wind domain who are based out of Europe, or solar, which are global. We also work with a bunch of Indian companies where we help them do the solutions in power, electrical and power electronics. In fact, the interesting part is our company has emanated from the electrical business group of Larsen & Toubro, which has a big legacy of doing electrical and power electronics for more than 35 years. And we are a 16-year-old company. And one of our strengths lies in the electrical power electronics offerings and the domains.
Yeah, very interesting.
Awesome. Yeah. Great to have you, sir. I remember I think in Bombay, Pune area, L&T is fairly well known, and they have a number of plants. And I had heard of course, L&T being in the construction and industrial business. But of course, after that, they've been dominant in software as well. And now it's only recently that I found out that they have the services division where they do all these other things that you have mentioned. So it's very nice for this industrial company to take its strengths and diversify in some sense, or to leverage those strengths for these diverse applications. Could you talk a little bit about your career growth? Did you always think that you would end up in power electronics, or was it sort of happenstance that you ended up choosing power or power electronics?
Yeah, so interestingly, when I was doing my engineering, I never liked electrical engineering, to be very honest with you. Okay, I wanted to be a mechanical engineer because in the 80s, that was the thing
I
to
see.
get into. And electronics was just coming up. But when I got into electrical, especially in the second year and the third year, when I started getting associated with the circuits part, the control theory, and in the final year, when I started learning about thyristors, because those days thyristors was the only device which we knew about. I started liking this field. I said this is interesting because it's
Right.
something which triggers your mind. It makes you think. And so in the final year, one of the driving forces was the project I did for my BE. It was a digital simulation of induction machine. We didn't realize that we were ahead of time because we did the DQ axis modeling of a electrical machine and built a DQ axis model and ran a Range Kutta fourth order method to model it for the starting current. And we actually tested it with a motor which was available from Crompton and Greaves. And our results were pretty
Wow.
close. So that was a point when I said I would go into power electronics and drives. Then I made up my mind to get into power electronics and drives. But after my bachelor's, I got a job with Tata Power Company, Tata Electric. And I got attracted towards power system protection and power system analysis. So when I went for my master's, I did under Dr. Syed Ali Mirbad, who was a leading person in power electronics. He was a student of Mr. S.B. Diwan. And I told him I wanted to work in drives. He said, well, we don't have major things going on in drives, but if you work in static power conversion, it will be good for you because it's quite holistic. And that's how I landed into static power conversion, and then rest is history. Then after my master's, my first job was at Black & Decker, where I got connected with Pradeep Bhagwat and Dr. Tumi Sebastian. And then I moved back to India, where I worked with Mr. L.S. Sanabhatti and Mr. Devdar. So that's how I got into power electronics initially into SMPS and high frequency, and then eventually into inverters, drives, and UPS systems, active filters, and the journey continued now into wideband gap.
Interesting.
Yeah.
So, would you say that
Yes.
there were some professors in your bachelor's, since you did a very, let's say, a very involved project and a very, let's say, advanced project in your bachelor's, would you say that some of your faculty members or professors played a role in shaping your interest there, or guiding you there? Would you say that?
Yeah, surely. Dr. V. Nagaraja, who was my project guide for my project, actually made us garner a lot of interest in digital simulation of induction machines. In fact, interestingly, we did not have a course on generalized theory of electrical machines because it was an elective which I had chosen out of. Okay, but Professor Nagaraj actually took sessions for us and explained to us. And once we understood it, it was pretty interesting. So he was one of the persons who actually helped me, started liking this field and made me sway away from mechanical into electrical, as I would put it. Okay.
You have been in Larsen and Toubro for how many years? And before that, you talked about Black and Decker and maybe one or two other places where you might have worked. So I was trying to understand which of these places was really influential or in your career, or somewhere where you learned most of your craft for power electronics.
Yeah, definitely. So it was in 87 to 89. I was doing my master's in Louisiana State University in Baton Rouge. And Dr. Mirbad was my major professor. And he actually had built up a very good lab. And I still remember the equipments we had. We had winding machines. We had general purpose PCB assembly equipment. He had a well-stocked components of semiconductors, passives and resistors, and of course thyristors. And he had made these golden bricks of half bridge, which we could, configure the way we wanted. So I learned a lot from him how to, optimize the design, because as you know, resources in the university are not as opulent as what we have in the industry, right?
Right.
Then after that, in 89 to 91, I worked with Black & Decker Corporation, where I worked with Pradeep Bhagwat and Dr. Tommy Sebastian, and they helped me shape my career a lot. I learned a lot from both of them, with Pradeep as well as Dr. Tommy Sebastian, and I would say that they were my gurus or the mentors who actually got me to start liking this field.
So where was this Black & Decker based at the time?
It was based in Baltimore in US,
Nice.
in Baltimore, in their headquarters, and I was associated with the Research and Applied Technology group. So Pradeep was our boss, and Tommy was my senior colleague.
Nice.
With
So,
whom I worked.
what kind of end products or applications were you working on at Black & Decker? I mean, we know of Black & Decker as a famous appliances and tools company. Anything in particular that you worked on?
Yeah, sure. The things which we worked on actually was the corded cordless battery charger. So the univolt charger of Black & Decker was the product which we were all associated with. Myself, Pradeep, Tommy, and bunch of other people. That was one of the products. Other product was a very high frequency. We built a 50 kilohertz inverter those days. Using MOSFETs, because MOSFETs were brand new. And using half bridge complementary commutation full ZVS.
Wow.
And of course, we then also worked with some bandsaw applications using drives for working on the bandsaw. So these were some of the applications I worked with Pradeep and Tommy in Black & Decker. I learned a lot from them, especially transformer design. What I learned from Tommy, and instant-to-instant analysis of a circuit with Pradeep, who made things look so simple, right? Because if you complicate things, people run away from the whole solution. So that was I was actually honored to work with both of them. And then due to family reasons, I had to move back to India, and I got associated with AppLab from '92.
I see.
And AppLab in Mumbai was one of the leading companies those days who worked in power electronics. In fact, they had a high power as well as a low power division, but I was working in their export oriented business in Seebs in Andheri. Where I worked with Mr. L.S. Sanabatti, who has influenced my life a lot. Because this is where I got into the resonant switching, inverters part of it, static switch. So the projects we did were absolutely a lot. We started with the active power factor correction, but having said that, the first active power factor correction, though not directly in Black & Decker, we had given a project to Texas A&M with Dr. N.J.T. Prasad. So in 89 or 90 frame, I had seen the first active power factor correction.
Right.
But when I moved to AppLab, I worked with Mr. Sanabatti. We had a soft switching active power factor circuit with a circuit for ZVS of the MOSFET, as well as reducing the recovery losses in the diodes. Mind you, those days we did not have silicon carbide diodes. We were all lousy diodes which used to recover a lot.
Yes.
Then we also worked on a phase shifted converter which went in for a German company, and they sold it for one of the real applications, which was a naturally air cooled rectifier, which was quite a challenging project those days. And we could hit up to 95% efficiency way in 93, 94.
So for listeners who may not really be able to appreciate that, can you say a little bit about why is it so challenging to have an air cooled system? And what are the benefits of doing that or being able to do that?
Sure. So in an air-cooled system, basically the removal of heat is always an issue. You have the semiconductors and the magnetics which heat up a lot.
Right.
In the fan-cooled system, it is pretty much straightforward. You can blow air on it, and you can remove the heat from the backside.
Yeah.
But here, the heat removal is only through the heat sink, which has fins, and the fins are usually mounted vertically.
I see. So we are talking about natural air or natural convection cooling, and no fans and no other fans. Cooling system. And
no fans, no other cooling system.
Was it was the objective here to remove the fan to improve, let's say, reliability or noise or some other issue there? Why was it necessary to have fanless system?
So these were operated in quite remote locations. So fan has quite a low reliability so there are two electronic components, fans and electrolytic capacitors, which actually impact the whole life of the system. So that was one of the reasons they wanted to have a naturally air-cooled rectifier. It was for a European application, and for German applications, reliability is the most important thing, as you know. So there we actually also worked with planar cores. We used the transformer using planar cores in 94 with the soft switching IC which TI had just launched, and we could actually deliver the product.
Wow.
And over there again, after this we worked on inverters, HF link inverters, we worked on DC link inverters for defense applications. And then myself and Mr. Sanabatti and Mr. Bhagwat, who also got associated with AppLab, who used to give us projects, we developed our own topology of asymmetric half bridge in a fly forward mode, as we call, and we published a paper in the IEEE conference. So we didn't want to patent it, we wanted to publish it so that people could use it more. That was one of the interesting highlights. Yes, and one of my colleagues, Mr. Girish Kamath, who used to work for AppLab. In fact, just before I joined AppLab, I used to work for a company next to them. So me and Girish go a long way. We used to discuss power electronics on the way home, and that's how we used to read papers, because those days we had no internet, right? Only hard copy was the only way to go and discuss them while we used to travel on the bus or something like that. So which was pretty interesting.
Awesome.
Yeah, that's really great to hear, because there were a couple of things that you mentioned that I thought I should add a comment to, because it rings a bell with some of my past experiences, and then I would ask the next question to you. And one is, you mentioned the thing about instant-to-instant analysis. And that's something for as a skill for a power electronics engineer, that's something so important that it's probably needs mentioning to younger engineers early in their career to develop this art of not just speeding through the entire functionality of blocks, but sort of freezing it instant by instant and looking at which device is doing what at which point of time, what happens after what. And it in a way comes from drawing waveforms, looking at waveforms in simulation, in experiments. And I'm glad you brought this up. Obviously it went past in like array of many different important things that you mentioned, but I thought I should bring that out. And the second thing which really struck a chord with me was about fans. And I'm just trying to recall, there was one of these doyens of the power electronics industry in USA. I'm forgetting the name. I'll dig it up later. But in one of his articles, he writes that at some point, he noticed that fans were essentially there to deposit dust into your electronics. And it took down the reliability of the electronics just because of the dust. Even if the fan is still working, it took down the reliability so much that he became fanatical about high efficiency power electronics designs without fans. So again, it's something that is coming up more and more these days with wide band gap and better and better devices. So I'm glad you brought it up. For my question that I wanted to ask is that while you work in all these different projects over the years, you worked with many, I guess, younger engineers. So I just wanted to know, it's kind of hard to master so many different things, because the terminologies that you easily throw up because you are experienced in it, let's say active power factor correction, or I don't know, 95% efficiency, wide band gap, it can be quite puzzling for young engineers. So what is your philosophy for helping people who are less experienced than you to come into the team and be able to help you build these kinds of complex sounding products and projects?
So basically, I still feel power electronics is quite a complex field, because you need to know magnetics, you need to know switching, you need to understand the semiconductors and even the mechanical, electromechanical packaging. So basically, when people say, like the students who are coming out of the colleges these days are pretty well informed and smart, much better than what at least we were, because of the World Wide Web, I would say. Okay, so they know what is power electronics, they know what is facts. Some of the acronyms what they use, maybe we also have to dig them up a bit. But yes, when an engineer joins, when we interview people, we ensure that they want to work in the field, in a certain field, and we try to place them there. So people who have done a project in power electronics or have taken electives, we kind of work with them, we explain to them basically. So it's more of a training session what we have. In our company, we have something like a global engineering academy, where we take them through some of kind of a classroom training. So in different areas where you want to, where you want the people to work. So power electronics is one of the area where we get them associated with these acronyms, tell them the basic functionalities. The best thing is to mentor them. What we do is we start usually with a testing project, because if you understand what you're testing, then you understand what you have to design so that you can test it. So that's the philosophy what So a lot of people, the first phobia may be high voltage, touching a high voltage, because people in college don't have
Right.
experience of touching high voltage, and it's pretty serious. You have to be the safety of the person who is working is of utmost importance to us, right?
Sorry to interrupt, but could you qualify high voltage? Because high voltage for power systems people and power electronics people and VLSI people are totally different things. So just to put a number on it.
So okay, so for power systems, anything above, I think 1.6 kV would be medium voltage, and anything above 4.4 or 6.6 kV will be high voltage. But for power electronics, I would say 230 volts or 400 volts, 230 volts AC, 400 volt DC, or 440 volts AC is a high voltage, because it can be fatal. Whatever UL says is beyond SCLV is basically what I call as a
Right.
high voltage, because it can be injurious to the person. And classically, if you are working in drives, at the most you go up to 690 volts AC, and at the most 800 volt bus or 1000 volts now. So these are the voltages where we want our engineers to work safely. Even how you connect the scope, like old times, I think you might remember we used to have a cheater plug or an isolation transformer on the scope, so you isolate the load and the scope so that you don't fry the whole thing. So these are the basic things which we actually tell them, and once they start testing, they get confidence, right? We help them analyze the problems, we guide them, and that's how we get them up to speed in their projects.
I see. So in parallel with all these external projects, I think what you're saying is that there is some internal process to develop, let's say, in-house technology or know-how or IP. Is that what you're getting at?
Absolutely right. So basically, as I said, we have 5 or 6 company-wide events. One is Tech Expression, where our engineers, we actually encourage young engineers to write papers on fields in power electronics. Like recently, we had 3 papers: one on a LLC converter, one on a matrix converter, one on a dual active bridge converter, which our young engineers wrote. Okay, and what ideas they thought, what they understood of that, and then we have a competition where they present it, and we choose a winner, so that way we motivate and we award them financially for doing this work. And also we also encourage them to have solutions and new ideas and any patent ideas. So any ideas they come up with, we encourage them to give it to our patent office, who conducts the patent awareness sessions for our employees. Then for every vertical specific requirement for industrial, automotive, aero, we nurture this, and these are the investments what we have. For example, we have a big power electronics lab in Mumbai, which can handle up to 220 kVA power rating. Wow. And we have dynes with a active front end which can feed power back like a phantom loading. We also have state of the art AC loads, DC loads, AC sources, DC sources. And in Bangalore, we have an EV lab to cater up to 25,000 RPM of dynes. And again, that is also in a mode where you can feed power back. We have ovens. We have a 8-meter cube oven, which even I can go in. We have EMI, EMC equipment internally in our organization for pre-compliance. So we know where we are.
Right.
We also have a 5G lab in Mysore, actually, where we have bought the whole spectrum. So all these labs, we put our engineers to work on them. Okay, and we like them to have a hands-on experience, and that's what teaches them a lot.
So you mentioned lots of things there, but let me ask a very specific question. When your new engineers are doing testing, of course, I'm assuming or making a, I'm sort of imagining that, let's say, the process is one of validation, or there's a specified test procedure or whatever, and then you have to check whether the equipment complies, does it comply to a certain extent, whatever. But one of the things that I have found and other people have told me is that being able to debug, or being able to, I call it Sherlock Holmes, get to the root cause of the problem, is a skill that very few students are able to develop on their own, and they need some, mentoring, they need some guidance. So could you talk a little bit about how, let's say, do you find new engineers or new graduates who join you already have that skill? If they don't, then what do you think is lacking on the education side? And then what do you do to, foster that skill once they're with you?
Yeah, that's a $1 million question actually, Dr. Abhijit. Because yes, a lot of engineers who come, they have not been exposed to it. So it's not their fault, right? Our
Right.
curriculums are a little bit regimented. Now, of course, that we are getting better at it. So yes, a lot of people just do the testing and come to us that this is not complying yet. Then we start asking them pointed question, show them the schematic. So let's get, for example, that the output voltage regulation is bad. So we then tell them, you open the unit, check at these points, see where there is a drop anywhere in the circuit. If not, fine. Then what can be the then they start getting into it. Then they say, we'll check the voltage at the feedback point, we'll check the reference, we'll check the gain of the amplifier, and then slowly they start understanding how the whole system works. So it's more to, so then they get intrigued that you go from a power level of say 400 volts to a signal level of 4 volts, or say 2.5 volts, and sometimes you can also deal in millivolt region. So that's how this is just an example. We develop some of the skills for people to understand and debug. There can be an issue about some blowouts in the MOSFET. So we tell them, you put a probe, how to put a probe, how to properly measure the voltage, what can be the reason. People don't know what is a leakage inductance, fresh students out of college. And we tell them how you characterize a leakage inductance in a transformer. How do you do a simple test like putting a huge cap to mask the transformer capacitance, give an excitation, find the frequency, what is the damp frequency, what damping factor you need. And once you tell them, they learn, they understand. And then the more serious kind of noise problems is which takes time for people to groom, because lot of things people look at it as a black art, because imagining common mode noise when you are out of a university is pretty tough. Even for an MTech student, fresh MTech student, it can be challenging. So we explain them what is the common noise, common mode noise, how it comes, how does it affect everything. For example, if you take a gate driver transformer, right, you have an isolated supply for high voltage, higher side gate switching, okay, and with wide band gaps, your dV by dt's are so high. So how is it important to keep the isolation capacitance across the transformer barrier to less than 2 picofarads? Otherwise we will be injecting all that noise into the control circuit. So all these things they learn because of experience. We mentor them, we guide them. In fact, I'm always open for any of my even trainees to come and knock on my door and say, fine, I need help here. I can spend time with him to explain what happens. We had some issues, very interesting issues like this. And then EMI, EMC, we have models which we have created. Some of our SMEs, subject matter experts who are in my team, have created good models with which we can tell our people. And then, of course, we tell them to go back to the drawing board, check it on the simulation. But old timers like me prefer pen and paper and calculations. So we also tell them that this is the rule of thumb, what you go with, or this is what the theory says. So this is how we groom them in, encouraging them to solve problems, come forward and see how things go. It's quite an involved, it doesn't happen overnight, it takes time. We need to have patience. Okay? But yes, eventually people start liking it.
And the student also has to have patience. The skill doesn't come immediately. And just to rephrase what you said, I think you mentioned a lot of points, but I think the distilled version that I'm hearing is when a student asks you a question saying it's not working, instead of giving them the answer or giving them the solution, I think you are giving them a question.
Exactly,
saying, why don't you try this, or why don't you check this, or why don't you look up this? So that's a really good point. Go ahead, Lalit.
Atul, you mentioned about blowing up of MOSFETs, and basically blowing up or burning any device is kind of like a inauguration of power electronics engineer. Like that is how power electronics tells you welcome. Once you do that, and then you try to build your setups in such a way that this doesn't happen, at least even if something goes wrong, there is no explosion, arcing, and of course sometimes it's unavoidable. So I just wanted to ask if you had any memorable burn with regard to any of these blowing up or explosions from which you learned something very interesting, and you could share that with us.
Sure. I had lots of them. Maybe if I start talking, we'll speak about it till the cows come home. But one or two of them I will definitely tell you. One of the burns and one of some silliest things what we learned from. In one of the units which we had given to our customer, the unit was working perfectly all right under linear loads. Okay, only under neon lamps. Okay, the unit was blowing, and it was blowing violently, I have to say the least. Okay. In fact, it was exploding. So we got the unit from the customer's place to our labs, and we started testing it, and we found on linear load it was okay. In short circuit it was okay. Only on neon lamp it was blowing, because short circuit was very well tuned. We had tuned it in such a way that we had 3 levels. One is instant to instant protection, where you check the current at every instant, and then you try out for some cycles, and if it still persists, you shut it down. So cycle by cycle protection, quasi instantaneous, and constant current. Whereas in a neon lamp, you see a huge surge. So it's basically kind of a form factor of the current waveform, which is totally different. And then we realized that the CT what we had to cater for a higher current, because for neon lamp it was actually saturating, and that was leading everything to. And again, short circuit, it depends on what point of cycle you do it. We can't control it, so we just got lucky that we were at the lower point of the sine wave, but maybe the neon lamp was turning at a peak of the sine wave, which was drawing huge amount of current. So that was one of the major blow-ups what we had in our lives. Another interesting thing was when I was working in the US, we had developed a 10 kVA converter with what I would say a pseudo neutral point clamp topology. You had a bridge with one point connected to the neutral, okay, and only one phase was blowing up, and it was blowing up badly. The whole system was a PMG, permanent magnet generator, to which the inverter was connected to, and inverter was stabilizing the permanent magnet generator voltage. So we were scratching our heads. I mean, we literally checked everything. The current sense was absolutely normal. We checked the level of saturation of our cores. No problems. Cores were perfectly well designed. Then what we found out was, then what we did was, I tried to go and change one of the MOSFETs, and one of the solder technicians told me, there's a very small gap on the driver IC. I remember IR2110. It was a semi-dry solder, I would say. Okay. On only one of the phases, and she said this IC doesn't look properly soldered. So I said it is on B phase, and that's what it is blowing. Maybe let's check that. Then I told her we had just graduated from through-hole components to SMD components, right? So through-hole it was very easy to see a dry solder. Where SMD, the solder point was very small, correct? So you really needed a lens and a good pair of eyes to spot it. So that was one of the things, and that was like, welcome to SMD. You are going to have more problems like this going ahead. But we blew quite a number of MOSFETs trying to find this problem. It was pretty weird, all the other phases were working properly. For one of the inverters, we also had a similar problem where we found out that we had actually done a good ground planing with a through hole connecting all the 4 layers. But for one of the layers, the through hole had come, the plating had come off. That's why ground plane got disconnected, and we had quite a severe blowout on one of the inverter MOSFETs. It was a single phase inverter. So these kind of things we learned, but yes, they were quite memorable burn-ins what we had. Okay.
I was just trying to understand the dry solder one for the SMD. So it would happen, let's say, in one card, but you had it in multiple cards, the same chip having dry solder. I didn't get that, or how was it?
No. We were developing the product, right? So we had only 3 prototypes. 2 were working perfectly. It was happening only in one of the cards.
In one, yes.
Okay, it was happening only in one of the cards. Okay, so we were confident that the design is working, but till this unit was also working, we couldn't say that fine, we have found a solution, right?
I see.
And then there was one memorable, one person I would also like to mention about who helped me shape my career is, of course, Mr. Devdar of Apple, who was a doyen of Indian electronics industry, who got electronics industry into India. But when I was working for Murata Power Corporation in the UK, my immediate boss, Mr. Paul Lee, he was a person who taught me how to go from a resistor level and a transformer level to a unit level and a system level. Because we had an interesting problem. We had made the first ultra wide range power supply. It was a low wattage one, which could go from 16 volts to 500 volts. That was the input range. Okay. Efficiency was good. It was working perfectly in our labs. I mean, we could not point anything. And in 2 revisions we had nailed it actually with everything. Even the UL design for UL was good. UL inspectors came and said that it should fly. We had done all the DVT, the oven tests, everything. But when it went to the field, it was the customer said that it is just not starting. Then when we went back to the specs, our customer wanted us to make a short circuit protection, which was latching. I think they were scared, okay, because we had told them we'll go into constant current and limit the power, but they didn't want that because it was a potted unit, naturally air cooled, so they thought the dissipation would be high. We said fine. So we got that power supply in and we disabled the short circuit. Again, it was working fine. Then Paul told me that fine. He said we look at the site report. The site report said it was mounted on some remote location in Australia, where the person was just putting the power supplies, connecting the fuse, and walking away. Okay. So he said the way we are starting is we are starting from a benchtop power supply which ramps up, which has a certain dV by dt ramp up. So we built a circuit with a DC circuit breaker, and we tested at different levels. And we found about 250 levels. If you put an impulse, if you put a step voltage, the power supply was going into a short circuit mode for some time and latching. Then we fixed the problem. We had to put an RC on the startup circuit to slow it down fictitiously. Okay, so these were some of these. That was quite interesting because the person had to travel 50 miles to remove the power supply.
This is an excellent point because I have heard this phrase before that starting is like the worst transient basically for any power converter.
Oh, yes.
If you are able to start up, that's already like a huge step ahead.
Absolutely. But again, one of the interesting things was one of the power inverters what we had sent to UK when I was working with AppLab. Mr. Devdar called me that it is showing weird readings, but Mr. Devdar, being an engineer, told me that the voltages are okay. We found one earthing screw was loose. I mean, a small screw not tied properly can cause humongous problems. And I was 32, 33 years old then, so we didn't realize that this can have such a hard-hitting consequences. So these are some of the things what we worked on.
Great. Amazing. Actually, just to add one more point that I think you may agree is that when a prototype or a product is designed in the lab, you as the engineer or the person designing it treats it like their baby. And you're very careful. Yes. You put it on the bench or you connect it to the supply, and then this person, I mean, the way I heard the story is they went and sent it out into the field, and this guy had a pickup truck, the site person, and he basically just tossed it into the back and then drove down a bumpy road, and it so he's not taking any of the care that you are taking in the lab. So it should work in that condition, not in your lab condition. So that is something that designers often don't really think about or even account for. And I think that answers your your loose screw anecdote a little bit, I suppose.
Absolutely. That's what we call as fox running a chicken farm. But again, we had escalations, we had blowouts in AppLab, but actually how to analyze it, I learned a lot from Mr. L.S. Sanavatti. He was so cool. He said, fine, if it is failed, let's first understand the failure. And he taught me how to analyze and pinpoint the failure perfectly. His analysis was something I've never seen. And he used to teach us, more important than he used to capture the waveforms, explain us, so we don't make the same mistake again. In fact, I was lucky to have worked with a person like him.
Wow. Yeah.
Because you are going to, in power electronics, you're going to have these problems, right? How carefully you design. But because at least we knew we were working on pen and paper. Now these days people work with MATLAB and LT Spice. Parasitics is something we have still not mastered in modeling. The day we master modeling parasitics, I think a lot of these issues will come down. But then the practical knowledge of the person will go low. So there's a fine balance. So it's more important is how analyze the problem, how peacefully or coolly you approach the problem, and that's the only way you can find out a solution. Because I know with the inverter in AppLab which was failing because of the CT, Mr. Sanavatti actually helped me a lot. On the site, simple things like how do you test a CT with a 100 amp CT with a 10 amp power source. He actually told us all that. We were very young, 4 or 5 years experience engineers.
So maybe we will shift gears a bit and change to a slightly different topic here, and that is about recruitment. So because you are now a very senior engineer, you probably have had years of experience trying to look for good young engineers. And what are some of the things that work for you when it comes to recruiting good students, and also in terms of what you look for in students so that they can try to work on those kinds of skills and that kind of knowledge?
I would stick to power electronics itself. We are facing challenges in recruiting good students in power electronics. A lot of people are not actually attracted to the field still. Of course, it is improving from what it was 10 years ago, because it's still considered as a blue collar field, not a white collar field, because you have to work with your hands, right? It is not a glamorous field. See, when you design a power supply, it's not glamorous as designing a an automotive or an aircraft, or even a hold for a lighting, right? You can go to the market and say, I designed this light, but we can't say I designed this power supply. So a lot of people, we are not getting good people who are pursuing their graduation or post graduation and doctorates. Number one. Number two is very few institutions have very good capabilities in power electronics. IITs, I'm leaving aside, because we cannot discuss about. They're the best in what you have in India. I would say in the world. Okay, the students and the professors and the commitment is super. I just don't even want to comment about it. But institutes like NIT or government engineering colleges, there's still a funding issue for running the labs, for having the equipment for people to test. Except one or two engineering colleges, where I found they've invested a lot. People are investing in telecom more. They're investing in they'll buy high tech laptops for C firmware. But in power electronics, the investments are still low. So that is a challenge we have. So basically, people, if we go to recruit, we get people from IITs, but we have earmarked some of the good engineering colleges in the country, okay, which are a mix of private as well as NITs and government engineering college. So this is one of the challenges we get. And other thing is, you get a smart BTech guy, in 2 years he leaves you, or in a year he goes to US to pursue his masters. Okay, in fact, they should realize that MTech programs in IITs are equally good. I can say that because I've seen MTech students, and they can also have an option of doing a part-time MTech while working, because that helps them. So that is one of the biggest challenges. And second challenge is, people veer towards MBA after working for a year. I don't know why. They start with a very high enthusiasm in power electronics.
Possibly, yeah.
Yeah, everything is financially driven. So that is one of the challenges we face recruiting good students. So good students, as I said, go to US, or they have planned to go to US, and they use companies as a stepping stone to learn things before they go for their masters. But having said that, we found that we have recruited some students with passion and who have been with us for 8 years. And the thing that differentiates them is the attitude with which they work. They might not be the brightest brains like BTechs, but they're very smart people. Don't get me wrong. But their attitude and the hard working and what should I say? You given a problem, they'll do everything what it takes to get after it. They will catch hold of me. They'll ask for some equipment, some investment, and ensure that they do it. And even if they get stuck somewhere, they can find their way around. We are getting those kind of people from, and it is interestingly from B-level towns. Okay, I'm not from big cities. That's the interesting change what we are seeing, and who are from good engineering colleges, private or government. But we are seeing those things changing. But again, for the PhD programs, yes, we are looking at recruiting PhDs for our organization. But our organization is a service-based company, right? So we can be working on a testing project, on a simulation project, or on the real project. Whereas PhDs mostly want to do a project which is more research-based. Whereas we work for our customers who want results very fast. Sometimes they want something cheap and dirty as a proof of concept. So what we do is, if we get a PhD or a good MTech people, we run internal projects for them.
Right.
For example, we are running a project on dual active bridge, on bidirectional CLLC converters, on some of the multi-level inverters, to keep them engaged. And we tell them, fine, you can do this program internally, we'll fund it, you help us characterize, build a solution, and we can take that solution to our customers to reduce their development cycles. So this is how we run research programs for the R&D teams. In fact, currently we have 6 initiatives in power electronics which are running, including hybrid energy, including EV charging, including onboard, offboard charging, and of course anything to grid connection. So these are initiatives we are actually running in our organization currently, and we have smartest brains working on it, MTechs and PhDs.
Great. So I think you mentioned a very wide application space, and I think as a service company you have to sort of cater to a wide variety of customers and applications anyway. But with your experience or over many years, what can you say about some of the dominant trends in power electronics and applications that you think are going to make it big in, let's say, the next maybe say 15 to 20 year time frame? Of course, EVs are there. People talk about chargers, and some of these, of course, flying cars are obviously like, unfortunately, the often berated futuristic concept that never, took off, no pun intended there. But on a more serious note, what do you think are really the trends that have a chance of making it big over the next 15 to 20 years? And specifically from an India-centric sort of perspective, because you've worked in India for a long time, and a lot of people who have worked outside India, I think don't really, let's say, they don't really focus on the differences that the Indian market or the Indian the customer really wants, and they're very different from, let's say, a US customer. So what do you think are the big trends over 15 years in power electronics focused on India?
Globally, yes, as you said, yes, the whole world knows EV is going to be the drivers with hybrids, hybrid aviation. But interesting part in EVs is onboard will slowly taper off. That's what I feel in next 4 or 5 years, because Chinese companies will start giving you onboard chargers which might be available at a any garage, or you just will be plug and play, and you just replace your charger with new one and go ahead. Maybe the EV offboard charging, because the current pain in the EV area is how do you charge your cars fast. Suppose my charger is taking 6 hours to charge my battery so that I can go 400 miles. How do I do that in 30 minutes? Because you go to a petrol station, in 30 minutes you fill up your gas, you're on your way, right? So the next area where I think people will be investing in will be an offboard EV chargers which are of high capacity. Okay. Then on electrification, like now we have seen everybody shouting about green gas effects and pollution. So we saw that cars are polluting, but cars are just one part of it, correct? There are a lot of other gas based equipments which are polluting the environment, like compressors, like hammers on the road, but you don't feel them because you don't see them so much. After we are done with cars and electrifying the cars and getting into, then the technologists will be searching for something new, so they will come on to these kind of equipments. Which
do you think commercial equipment, agricultural equipment, construction equipment? Oh, I see. Okay,
exactly.
That's
yes, exactly. So those kind of equipments will have to be electrified, and of course hybrid aviation. Now I don't have much insight into aero industry, but yes, there's a talk of going in more electric aircraft from a standard what you have for your compressors or rotary compressors to like lube motors, or having more electrification on the drive side of things. So there are, but it's a slow ramp up which will take some time to come to fruition. Other thing is 5G. With 5G coming in, you will need more power to power the 5G and then subsequent 6G mobile towers or mobile equipment, and that will be one of the areas, because given the constraint, the whole thing will be going down to how do we do it in the same size with the higher efficiency and higher power, and that is one of the areas. Now coming back to India, Indian market is totally different. I would say it's a paradigm shift with respect to the global market. One is the cost, right? One is the cost, one is the availability, and one is the efficiency, and of course the operating conditions, the temperature and the dust. So and other thing is the bureaucracy. Maybe bureaucracy is going to, as they say, necessity is the mother of invention, right? So for example, if you want to set up a EV charging station for a bus maybe in just outside IIT Dharwad, and each bus takes circa 250 kilowatts to charge, right? You get 10 buses at a time, you have 2.5 megawatts to charge. Now if you go to Karnataka Electricity Board or MSCB, Maharashtra Electricity Board, to put a new transformer, they will take 6 months, right? And to change the wiring. So for Indian conditions, what's going to happen, what I feel is you're going to have renewables, battery energy storage solutions. So if the transformer can give, say, 100 kilowatt, you add a battery energy storage solution of 2.5 megawatts, where you beef up the grid, or as you say, do the power shaving. When the buses are being charged, you draw the power from the batteries. That batteries can come from solar, wind, or even, and so the batteries will be discharged in charging, or even they can feed to the domestic or the other consumers which are based on that particular distribution area. And in the night time, when utilities typically want you to draw power to keep the receiving end voltages under control, they can be used to charge the battery. So I feel this is going to come in a big way. Then hydrogen fuel cell based inverters will come in a big way because they are again pollution free, and they have a long life at the end of the day, because they go for 80,000 hours to 90,000 hours. That's what. And other thing is, as far as EV chargers goes, we Indians are very good at innovating things. If you go to an auto rickshaw, he doesn't want an onboard charger in his vehicle. It costs money. It increases the cost of the vehicle, right? Maintenance. So he might carry his own onboard charger, where he sees a plug point, he can plug in, charge his battery, and move on. And that's the best way, correct? Because that gives him flexibility, right? So that is an area where making these devices portable and then doing the billing of this with various protocols, which is a challenge. But that is on the communication side, so I will not go for it. And of course, in grid tie inverters, as I said, VAR compensators is something what Indian markets will look at, because you can use the same infrastructure. If you can use it, you can utilize the same infrastructure. That is going to be the whole thing, because building a new infrastructure will definitely take time and money. So if you have a VAR compensator, you reduce the RMS currents in the transmission lines. If you have a grid tie inverter, where you utilize your generation capacity, because if you generate closer to the point of load, then your savings in terms of the transmission losses are basically gone, right, from the generation station to. So I think these kind of things will come in, will be prominent in India. Maybe not in the immediate next 2 years, but in 3 to 4 years. That's what I feel. And then again, data centers, because India is a hub for data centers, right? Data centers are also, as the storage area increases, the power supplies for data centers, or they might replace the generators with hydrogen fuel cell based inverters. So these are the areas where I feel in India we'll have a lot of things coming on, especially on the transmission side. EV, yes, the world is working on it, and we'll leverage what we have. That's my take.
The reason we ask your perspective on a 15-year time horizon is someone who's, let's say, just about to enter a graduate program or even a bachelor's program in engineering is typically going to be at their let's say at the middle of their career in about 15 years, right? So they're going to be finishing maybe 4 years of their bachelor's, 2.5 years of master's, and then couple of years of experience, and then they are going to be the ones driving the real growth in all these new fields that you talked about. And the reason we ask is our listeners who are probably getting into the field right now, what is it that they have to look forward to? So I think you've covered a fair variety of interesting challenges, and I just want to mention that India especially, of course, Europe and US have done a lot in terms of interactive grid. So for instance, as you said, VAR compensation, or just doing, let's say, phase-to-phase balancing, or just injecting power to keep the peak load down, or transmission congestion, right? Just cutting down on that. I think there's a big thing to be said for that in India, where we are cost constrained, we are infrastructure constrained, and of course, as you rightly mentioned, there's some red tape impedance as well. So I think some very interesting and very good points for us to think about.
I would just like to add one point. So especially for people who are coming out, I think the focus areas from technology's point of view would be, of course, wideband gap. It's very easy to say I want to switch at 1 megahertz. There are a lot of problems associated with it. Believe me, switching wideband gap is a totally different art compared to switching an IGBT. We have transitioned from SCR to GTO to transistors, IGBTs, and to MOSFETs, and we have felt the pinch and the pain. Even IGBT to MOSFET, there's a huge difference. The tail currents of IGBTs have vanished. They have become positive temperature coefficient devices now. The MOSFETs then dominated, but now going to wide band gap, especially with the low reverse transfer capacitance, how you lay out your gate circuits. So this is something what I think it should be. I would actually say there should be a kind of a course which should be introduced in the universities. Because I was lucky to see a video. It's an old tape from Rudy Sevens and Gordon Bloom, who actually had explained how you drive a MOSFET. It was a very interesting video which I had seen in Black and Decker. And number two is the magnetic materials, with because that is still going to, and AC losses, because the moment you increase your frequency, your magnetics have to be designed properly. Eddy current losses, how to use Dowell's curves, what are the new material. Like Fraunhofer recently has jacked up the power densities to 4 kilowatt per liter using nanocrystalline materials from Hitachi for PFC and EMI. So how you use them, that is another area which I think, and of course resonance switching, that's the only way, bidirectionality and resonance switching. So these are from the technology or the topology's point of view, I feel is going to drive the future for next 5 to 10 years.
Wow, it's just amazing how many different, let's say, key technological terms you have covered in such a short span of time, because each of those keywords that you mentioned, like it is like an entire area in itself to explore. So I think that would be very useful for our listeners to just use those as keywords to think about what is it that they need to learn to be able to let's say implement these kinds of new technologies. So
and it's going to be a task for us to put the show notes and resources together
with all the acronyms,
try and even successfully all the acronyms, and to try and capture, I think good reference points for all of the things that you have mentioned. So thank you once again for taking the time to speak to us despite your obviously very busy schedule.
No, I thank you for giving me this opportunity to speak to you, and I would like a lot of more people to come into power electronics and let it be an attractive field where people say that I want to get into power electronics and develop new things, because you can get power but to convert the power is the whole art.
So in conclusion, for our listeners, where can they find you online? Are you available on LinkedIn or any other social media platforms?
Yeah, I am available on LinkedIn. I'm a little bit laconic on LinkedIn, but I need to update my profile also. But yes, I'm available on LinkedIn. I'm available on my email.
Perfect. And so we'll have a link to your profiles and email in the show notes in case any of the listeners want to reach out to you. Thanks very much once again.
Thanks for the